Afternoon to the East and good morning to the rest of the country. My name is Jeff Clayton and I'm one of the Vice Presidents of the AAS. I'm very excited about the two speakers we're about to hear from. We have all been reading about the satellite constellations and looking at the images of the Starlink satellites. And these and other satellites are also threatening to further encroach on the radio spectrum bands that are used for astronomy. Our two speakers are going to discuss both these topics. Our first speaker is Dr. Sandra Cruz-Pol. She received her PhD in electrical engineering from Penn State, working with passive and active satellite sensors, studying atmospheric gases and sea surface emissivity. She was the program director for the EARS, Enhancing Access to the Radio Spectrum program at NSF, where she was also a spectrum manager. She was also appointed as a member of the US delegation for spectrum management to the International Telecommunication Union in Geneva. She is currently an NSF program director for the Engineering Research Centers program. Our second speaker is Dr. James Lowenthal. He received his PhD in astronomy from the University of Arizona, studying line emission from galaxies at high redshift. He was a Hubble Fellow at Lick Observatory and is now the Mary Elizabeth Moses Professor in the Department of Astronomy at Smith College. His research interests include high redshift galaxies, QSO absorption line systems, galaxy formation and evolution, starburst galaxies, and exoplanets. As James recently pointed out, he and I are both past chairs of the AAS Sustainability Committee, where we have long considered the need for virtual meetings. Who knew it would happen so soon? Anyway, I just want to say that you can submit your questions for both speakers during their talks. We're going to wait and have all the question period at the end of the second talk. And there will be an extra 15 minutes added on for the speakers to answer additional questions. So we have lots of time. So I'd like to just welcome our first speaker, Dr. Sandra Cruz-Pol.
Okay, okay. Thank you. And I want to, first of all, thank the American Astronomical Society and its vice presidents for the invitation to this plenary. I'm really honored and very excited to be here today. Even though it's virtual, I want to say that this is the virtual platform that is most impressive. You've done a great job, and it is the closest to a real physical experience that I've seen so far. As you may know, I'm a professor at the University of Puerto Rico, Mayagüez, but I'm also a program director at the NSF. So I want to make clear that any information or opinions that I present here are my own and not necessarily the views from NSF. Today, I'll be talking about what is the radio spectrum process that allows us to study the cosmos, among many other applications. In fact, all of us use the radio frequency waves every day, numerous times throughout the day, for our personal activities like texting, GPS, and probably to see this Zoom video via Wi-Fi. Indeed, if our eyes were able to see the RF signals around us, we probably wouldn't be able to see past a few meters ahead of us. So that's why it's so important to know about how to regulate this so that we can share without RFI. So this is the outline of what will be covered in my part of the keynote address. After a brief introduction, I'll go through the radio regulations at the national and international levels, then tell you about what spectrum managers do, and next I'll go through some basic concepts and acronyms for radio astronomy. So let's start. First of all, it's very hard to imagine a world without radio spectrum frequency devices. There will be no hurricane monitoring, no postal service tracking, no weather forecasting, GPS, solar storm prediction, cell phones, mobile phone applications, Wi-Fi, FM radio, etc. In fact, I don't have to imagine because after Hurricane Maria hit the island of Puerto Rico, we didn't have any of these for many months and no electricity. And it feels like you're living in the 19th century, except we didn't have water either. But anyways, this also goes to show how much we depend on these things. And every day, more and more devices rely on the spectrum, even vacuum cleaners, baby monitors, IoT devices. All of these are only possible thanks to the sharing of the RF signals with minimum radio frequency interference. The radio frequency spectrum is conventionally defined as a subset of the electromagnetic spectrum, encompassing frequencies from 3 kilohertz up to 3,000 gigahertz, according to the ITU regulations. However, recent studies extended to the frequencies approaching the edge of the far infrared into the higher terahertz. We humans can only see a tiny visible part of the spectrum, yet we can also perceive IR waves in the form of heat. Most television sets use IR receivers on the remote controls, and also night cameras use IR to detect us, humans, because we emit this frequency more than any other one, due to our body temperature as given by Planck's law. Planck's law also helps radio astronomy to detect different molecules. But IR is not part of the RF spectrum. The RF spectrum is the part that includes microwave, millimeter waves, and other things such as included within this. Numerous scientific and engineering applications also use RF spectrum, including linear event monitoring to forecast extreme weather, rain and wind remote sensing for renewable energy, cybersecurity for extra bandwidth needed to encrypt information, soil moisture monitoring for agriculture, and firefall mapping, just to mention a few. The first thing we need to understand is that the RF spectrum is a limited resource, yet increasing applications and devices rely on it for operation. Therefore, these radio regulations are constantly changing in a process led by an international agency. So that's why we need radio regulation. Through all the previous examples, we can see that engineers and scientists can design and build amazing instruments that use radio waves to help society in so many ways. But it doesn't matter how good and expensive these devices are if RFI deems our sensors unusual. That's why RF spectrum management is so important, which is the process to ensure that all users can share it efficiently for the benefit of society. This here is a section of the US table of frequency allocations. Each color represents a different use, which we call a service. Here you can see radio astronomy in yellow within the 1.4 gigahertz region, where the spectral line for the neutral hydrogen molecule lies. Each country has a different frequency allocation table or FAT, which might be different from each other. The tables summarize how the spectrum is used and shared among numerous users. I will tell you a little bit more about that later. So as I said, radio regulation is very important and is led by an international body. The United Nations has a specialized agency for this, the ITU, or International Telecommunications Union. This is particularly important for global coordination, as is the case of satellite licenses, which we'll be talking in the next part of the keynote. Since satellites circulate all over the Earth, crossing international boundaries, and they have to be agreed upon with this international agency. The ITU divides the world into 3 regions, as shown in this map. The Americas are in region 2. Because applications and uses of the radio spectrum change so rapidly, there's a need to revise them regularly, so the ITU coordinates the work of World Radio Communication Conference. This is held every 3 to 4 years, typically in Geneva, and typically lasts 4 weeks. The radio regulations have international treaty status, whereas the ITU recommendations are non-mandatory unless they are incorporated by reference into the radio regulations, but they're generally followed out of convenience. For instance, a very important ITU recommendation for radio astronomy is ITU RA 769, which presents, among other things, level of interference detrimental to radio astronomy for different systems and for spectral lines, for continuum, VLBI. So sometimes the radio regulations have exceptions for specific regions, and this is where the national level comes into play. The US is a special case because it has 2 agencies that regulate the spectrum. The FCC, or Federal Communications Commission, is for non-federal users. The NTIA, or National Telecommunications and Information Administration, is for federal users. The structure of the US process to prepare for the World Conference replicates the international committees and working groups, both within the FCC and the NTIA. As part of the US process to change the radio regulations, the FCC has what is known as the Notice and Comment Rulemaking. In this process, the FCC gives the public a notice that it is considering adopting or modifying the spectrum rules and seeks the public's feedback in order to hear comments from the community. This is done by publishing an NPRM, or Notice of Proposed Rulemaking. The process actually starts with an NOI, which is a Notice of Inquiry, to seek information in order to better prepare the NPRM. The NPRM may be followed by a future Notice of Proposed Rulemaking, or FNPRM. And then this happens if the comments led the agency to make considerable changes to the original proposal. Any interested party may comment. The FCC typically gives 60 days for public comment and an additional 30 days for reply comments. The final rules are issued in what is called the report and order. So NTIA manages all the spectrum assigned to the government. This is done with the IRAC, or Interdepartmental Radio Advisory Committee, which is composed of representatives from federal agencies that use the spectrum. The NTIA shares the IRAC, and for instance, one of the subcommittees coordinates the National Radio Quiet Zone. Now let's take a closer look at the section of the frequency allocations table. For each frequency range on the table, there are different colors. Each color represents a service or use. When there are more than one color, it means that several services are sharing the same frequency range. If the service is written in capital letters, it means that it is primary. If it's lowercase, it's a secondary service. And this is in relation to the priority of using the band. And I'll talk a little bit more about that later. So now, for more detail, the NTIA publishes a table in this format on its Red Book, or Manual of Regulations for the spectrum, showing each particular frequency range. For instance, here it's for 21 to 27 gigahertz, around that. And on the left column, they list the international allocations. On the right column, they list the federal and non-federal allocations. They also use uppercase and lowercase for primary or secondary, and also note these numbers, which are called the footnotes. The footnotes contain very important information, such as geographical exceptions, power levels, and much more. The international footnote starts with a 5. If it starts with the US, it applies to federal and non-federal government allocations. If it starts with NG, it's only non-federal government licenses. If it's G, only federal government. This is an example of an international footnote, very important for radio astronomy. It says that all administrations, which basically means countries, are urged to take all practicable steps to protect passive services like radio telescope from harmful interference within these frequencies listed here. This is an example of a US footnote. In this one also is trying to protect all the services passive, which is radio astronomy, that use these frequencies. This is yet another example of a footnote from the US, which lists all the location of the several radio telescope and which frequencies they use. So as you can see, they have a lot of important information. And the spectrum managers take all this information, all this knowledge, and many other factors into account when considering the changes to the radio regulations. In fact, there are spectrum managers at all kinds of companies, such as Boeing, Google, Nokia, and at government agencies such as NOAA, NASA, FAA, etc. They are in charge of managing the spectrum, attending spectrum meetings at national or international levels, working with frequency assignments or licenses, and protecting the access to the RF spectrum for particular users. At the NSF, we have 2 people designated at the NSF Spectrum Managers, Dr. Ashley Soderer and Jonathan William, who, by the way, will be here participating in the NSF Town Hall event in this conference. So I encourage you to attend and ask them any specific questions you might have. Here is their contact information. And lastly, I'd like to cover some very important concepts used for radio astronomy within the RF spectrum management world. As I mentioned before, there are 2 types of allocations. Here's the definition for primary, which is the one that is given priority and needs to be protected. And secondary allocations are services for which they have to protect primary allocations and they have to accept interference from primary users. Another definition is the UNI, which is services that FCC establishes that they can transmit without having to apply for a license. It means unlicensed national information infrastructure, and every country defines their level of allowable transmit power, bandwidth, whether they can work exteriorly or indoors only, and many other factors. So they all have access to the same frequencies without protection. And this is probably why sometimes my Bluetooth mouse stops working when somebody turns on the microwave oven. They both use 2.4 gigahertz. Another important definition is sensor type. Active sensors, such as a radar, have a transmitter that sends an electromagnetic signal, illuminates a target, and a receiver that measures what bounces back from the target. Passive sensors don't have a transmitter. They only have a receiver that measures basically natural thermal emissions like noise power. And their design allows measurement of signals smaller than the noise introduced by the radiometer itself. So that makes them very vulnerable to RFI. Another important thing to note is that passive radars are not passive sensors. They measure signals that bounce back from other transmitters and other targets, not natural emissions. The receive observatory can be used as both passive and active radio telescope. So in this image, you can see that both passive and active sensors can experience interference, or RFI, which is shown here in red, causing data loss. So one challenge is the aggregate effect, which means that it's the accumulated radiation from several emitters. And another challenge is when the RFI is of similar level of observable data, which corrupts the data that is then mistaken for valid data, leading to possible flawed conclusions. Other useful term definitions related to RFI include out-of-band emissions, which are immediately outside the necessary bandwidth, spurious emissions, which are non-intentional emissions also, and they can be both caused by harmonics or other intermodulation products. And then there's also the definition of harmful interference, which is any emission that endangers the operation of another device or service. And as I said, in the RF spectrum world, we don't say use or application, we say service. And this is just a partial list of acronyms used in the spectrum world. For instance, FSS means fixed satellite service, which is used for geostationary satellite orbits. RAS means radio astronomy service, which uses mostly passive ground-based observations, but also sometimes satellites to study space. SRS stands for Science Research Satellite Service, which sometimes includes near Earth and deep space satellites. And there are numerous other concepts and acronyms. In fact, I teach a semester-long course on this, so it's impossible to cover that in 15, 20 minutes. But this is the end of my part of the presentation. I just want to leave you with some reference that you can download for free if you want to find out more. For instance, CORF, which is the U.S. National Academies Committee for Radio Frequency, of which I had the honor of being a member for 2 terms, published a book called The Handbook for Frequency Allocations and also the Spectrum Management for the 21st Century. They're both free online. The National Academies also published a strategy for active remote sensing and I mean, the amount of radio spectrum, of which I'm a co-author, is also a very good source. Another excellent resource is NASA Spectrum 101, and of course the Red Book, we call the Red Book, but it's the NTI Manual of Regulations and Procedures for Frequency Management. They're all available free online. So I hope you have a better understanding now about the importance of the radio spectrum and the process, and that have inspired you to learn a little bit more about that. So thank you very much. And now I will leave you with Professor James Lowenthal.
Thanks very much, Sandra. We're just going to switch screens here, and we're going to have James's talk, and then we'll go right into questions. Take it away, James.
I think you're muted, James.
Am I still muted?
James, you'll want to swap your screens. We're seeing your presenter. There's a swap displays button at the top of your screen on the left.
We're hearing you fine, James.
Thanks. Let's try this. Okay, great.
Looks great.
Great, that's what I was trying to ask when I was still muted. Thank you, Jeff, and thank you, Sandra. I want to start by expressing my solidarity with those suffering from the distress and violence of recent events, especially the death of African-American George Floyd at the hands of Minneapolis police, as well as the long-standing harm and injustice of institutional racism. My life as an astronomer changed a year ago on the night when I saw this. I knew immediately what it was because I had seen this video earlier that day, but still, I really wasn't prepared. Of course, those were Starlink satellites, the 60 in the first launch. There have been 6 more launches since then. Each launch of 60 satellites puts the satellites at an altitude of about 300 kilometers. Here's one batch of 60 being released from the spacecraft shortly after launch. There will be 26 launches total, roughly, finishing with around 1,600 satellites by the end of this year. Shortly after launch, the satellites slowly separate. At first, they're very bunched up. They slowly separate into this orbital ring. This is just one of the launches. And then they're allowed to process to different positions and actively controlled to orbit raised to their final orbit of 550 kilometers. Here's a close-up of what one of the Starlink satellites looks like, the business end, the chassis, with the antennas, communication between satellites and uplink and downlink to the Earth. Here's a little bit zoomed out, showing the whole solar panel. This is big. Each solar panel is 8 meters long. The chassis itself, 1.5 by 3 meters long. These are pretty big satellites. The goal of Starlink, of course, is to provide fast broadband internet coverage all around the globe, where fast means for a London to New York communication, 46 milliseconds, what they call low latency. All right, what are some of the impacts of mega-constellations of low Earth orbit satellites like Starlink? Let's consider 3 different kinds of impacts. Mostly what I'll talk about is the impacts on astronomy. I'll also touch on impacts on the human experience and possible impacts on natural ecosystems. By LEO, low Earth orbit, what we mean is orbits that are within about 2,000 kilometers of the Earth. And it's pretty crowded, as you can see here. This map is a zoom in showing the low Earth orbit objects among the roughly 20,000 objects bigger than about 10 centimeters that are tracked by the United States Space Surveillance Network. And here we can see how these numbers are growing in time since the start of the space age in the 1950s up to today, where there are around 20,000 objects. And the step functions you see here at 2007 and 2008 are, or 2009, are from collisions of satellites, intentional in one case, unintentional in another, where a single satellite or two satellites turned into thousands of smaller satellites, providing the total now of 20,000. Only about 2,000 of these, the blue line, are actually working satellites. Most of the rest is debris. This is about to get much worse. We've got 20,000 now. We're about to go up several jumps of more tens of thousands in the very near future. What does all this look like from the Earth? Of course, the way we see satellites is reflected sunlight, and it helps if you're in a dark sky. So the best situation then to see satellites is if you are standing somewhere on the Earth that's in the night side, your sky is dark, but the satellite is in the sunlight. And the most likely situation for that to happen would be twilight, morning twilight or evening twilight. Keep in mind, of course, that the shadow of the Earth is not a cylinder, but a cone, which means that higher elevation orbits of satellites spend less time in the shadow, more time in the sunlight. So we put all this together and we see that the visibility of a satellite, whether you see it or not and how bright it looks, depends on a number of different things: the altitude of the orbit, the inclination of the orbit, the time of day and year, the position of you on the Earth, and the details of the satellite. How big is it? How bright or shiny is it? What shape is it? And how does it present those shapes, the different facets to the sun and to the Earth? So what is the attitude of the satellite? And considering satellites just in the low range in LEO, say 500, 550 kilometers, they're going to look brighter because they're closer. They're going to move faster across your sky because they're closer. You'll need more of them if you're trying to provide lots of coverage for communication. They'll be sunlit less, and they'll have shorter lifetimes. Their orbit will naturally decay due to friction from atmosphere in maybe a few years. Whereas at the high end of LEO, say 1,300 kilometers, where many operators are putting their satellites, the satellites might have a lifetime, natural lifetime, longer than 1,000 years, even if they're required to deorbit within 25 years. We have to consider all three phases of satellite life: when they're launched, and then orbit raising to their operating orbit, when they're operating, and then when they deorbit. All three of them can potentially affect astronomical observations. For example, SpaceX estimates that around 300 of its Starlink satellites out of 4,400 in its second phase, around 300 could be in transit, raising an orbit or deorbiting at any one time. But can we predict how many satellites of all of these objects we're talking about are visible at any one time? Certainly, and this is exactly what my colleague Pat Seitzer at the University of Michigan does. In this plot, he is showing the number of satellites visible versus time. This is representing one night. The middle of the plot is midnight. The red line on the left is evening twilight and the astronomical twilight, and the red line on the right is morning twilight. And the blue line shows the total number of satellites visible, which is to say high enough above the horizon you can see them and illuminated by the sun. What Pat's using for input here is the total catalog of tracked objects, nearly 20,000 objects. And you can see that even at midnight, as many as 600 satellites are visible in your sky, where your sky is here modeled to be the equinox seen from CTIO in Chile. Over 600 orbiting sunlit objects larger than 10 centimeters. But of course, most of them are very faint. Most of them are not going to be a problem for astronomy, and certainly far below naked eye detectability. What if we limit this just to Starlink satellites? Then the picture looks like this. Here's a night in Chile. That's the shortest night of the year, the summer solstice, December 21st. And we see that at midnight now, the Starlinks, which are in low Earth orbit, again, 550 kilometers, at midnight, none of them is visible, zero, for several hours around midnight. But for several hours around the twilight periods, both evening and morning, there are as many as 9 satellites visible. So what this means is as late as more than an hour past evening twilight, you might be able to see a couple of satellites crossing the sky. They'll take maybe 5 minutes to cross the sky, be replaced by another few, then another few, then another few. We can also play a game here and test the scenario where satellites are placed into orbit at the higher range of LEO. let's say 1,150 kilometers. What would the Starlinks look like if they had been placed at that elevation? And here the picture is much different. Here we see that in the twilight hours, we might have as many as 25 bright Starlink satellites visible at any one time in the sky, and even at midnight, a minimum of 10 Starlinks visible at any time. Why should we worry about this? If there are already 20,000 objects in the sky being tracked. And of course, the answer is obvious in this picture that I took here in Northampton, Massachusetts, of Starlink satellites passing through the Ursa Major region of the twilight sky. They're bright. These are, of course, satellites. You can see how closely spaced they are. This is speeded up about 8 times in the time lapse. These are satellites that were launched recently. This is seen about 3 weeks after launch. They have not gone up to their final orbit yet. They are still very bright. They're as bright as the brightest stars in the Big Dipper, easily second magnitude. The Starlink version 0.9, which is, say, the satellites that have been launched already, and 1 or 2 of the next launches probably, they are brighter than 99% of preceding satellites. Previously, until Starlink, there were fewer than 200 satellites visible to the naked eye out of those roughly 20,000 objects that are tracked. Now, already, Starlink has added more than 420 naked eye satellites, more than tripling the number of objects that artificial satellites that you can see with your naked eye. That may be small potatoes compared to what's coming. Think about 10,000 bright satellites or 100,000 bright satellites, and we begin to see what the magnitude of the challenge is. Here's a simulation of real-time view, naked eye, of the same part of the sky, the Big Dipper, showing Starlink satellites. Here's one crossing, about to cross Mizar, followed by another one in a similar orbit. Here's one, I hope you can see my cursor. Here's one following a different orbit, soon to be followed by another Starlink in the same orbit. This is the view we would have if Starlink satellites all have the same design and brightness as the ones that have already been launched, and if there are only 1,600 of them. But whenever you see this picture, imagine, think to yourself, could be 10 times more within the course of a few short years. Okay, that's naked eye. What would it look like if you took a big telescope and zoomed in on one tiny little piece of the sky, or this whole view for that matter, and the satellite happened to cross your field of view? Well, of course, it's going to look like this. In this CCD image on the left, there are actually 2 satellites that have crossed, one bright one, one faint one. And you take a cut across in the CCD image, and you see the bright one is totally saturated. You can see in the plot it's been chopped off here like a tree. Those pixels are completely unusable. The information is totally lost there. And it might be worse. There might also be enough, it might be bright enough that there's crosstalk induced in the CCD electronics, producing ghost images. There might also be ghost images from internal reflections if it's bright enough. And there could be residual images. So the next picture you take actually shows a memory of that satellite track. This has already happened, of course. Here are some well-known examples of, sorry, let's see if I can, oh, okay, I don't know what's going on here. It looks as if I have crosstalk in my CCD. These are 4 examples from major observatories of photobombing by Starlink. All of these cases show Starlink satellites shortly after launch, when they were still very bright, 0, 1 second magnitude, and still tightly bunched together, which is why they all appear in the same fields of view here. We can consider a somewhat longer term scenario and ask, well, what would the satellites look like once they are at their final orbit and spread out more? And how bad are the impacts going to be? Let's take a test case, possibly the worst case, Vera Rubin Observatory, nearing completion in Chile, with a field of view 40 times the size of the full moon and 3,200 megapixel camera. What would it see if a Starlink satellite passes across this field of view? This has been simulated by VRO Here's one of those simulations. The bright streak in the middle is the satellite itself, completely saturated, so bright that it induces electronic ghost trails from crosstalk in the CCDs. And these electronic ghosts are very difficult to deal with. It turns out that they're nonlinear. It's difficult to model. They're practically impossible to remove. Even if the trail is not quite bright enough to induce those strong ghost trails, the saturated pixels are still completely lost. The satellites need to be fainter than at least 7th magnitude for VRO to deal with these ghosts effectively. And even in that case, the trails are still completely saturated. So could VRO dodge the satellites if we knew exactly where they were? So SpaceX provides that information. You put it into your scheduler and ask, could we just dodge them? VRO has done extensive modeling to try to answer that question. And here we see that in the sort of worst case scenario with 48,000 satellites, not just 2,000, and seen at twilight, 90% of VRO fields would be crossed by satellites. And we might ask, well, how many observations would be possible? VRO has a scheduling algorithm that says, okay, now move the telescope here, move it there. How many of them are possible? Here's a plot showing that as a function of time of night between twilight and midnight. The blue line shows with no satellites. The green line shows that with 48,000 satellites, most VRO observations would not be schedulable. This is a major collision of technologies. Just when we are developing deep, fast, wide field sky surveys, along come LEO satellite mega-constellations. Of course, radio astronomers have been dealing with this for a long time, as we just heard from Sandra. This shows the allocation of the radio frequency spectrum just to radio astronomy. And this shows the crowded field of the whole radio spectrum with radio astronomy just holding onto that narrow little slice of the pie. And of course, satellites make the RF spectrum only more crowded because they have to communicate with the Earth using radio frequency communication transmission. As Sandra mentioned, protection of the radio sky for astronomy has been a fortunate fact of our life for decades and decades. And there's this whole structure that Sandra described to guarantee that protection as best we can. And radio astronomy has always had a seat at the table at international discussions, including the World Radio Communication Conferences, to try to protect our little piece of the spectrum. What does this look like for the optical infrared sky? Here is a chart of the framework of protection for the OIR sky. Oh, whoops, there is no protection. There's nothing. There's no such regulation. There's nothing protecting astronomy from the incursion of light pollution or now low Earth orbit satellite constellations. Of course, satellite operators need permission to put their satellites into low Earth orbit. In the US, they need permission from the FCC, from the FAA. They need ITU agreement as well. But they do not, unfortunately, need to ask the astronomers. They don't have to ask the AAS or the IAU or the International Dark Sky Association. Since the launch, first launch a year ago, the AAS has spent a huge amount of time and effort and resources on this issue. And when I say the AAS, I mean largely Kelsey Craft and Joel Perriott in the executive office, so a big shout out to them. Here are some of the activities. It's taken place mostly through the aegis of the Triple Threat Committee, the Committee on Light Pollution, Radio Interference, and Space Debris, and also a smaller working group that I'm on. The AAS has issued a statement, has ongoing discussions with the IAU and IDA. It's made briefings to Congress and to the national academies. It's conducted a webinar just last month. It's planning a workshop for later this month. And it's issued a survey of impacts on astronomy, a survey of major observatories around the world. So I just want to give you a quick view of some of the responses from that survey. There were 7 questions. We got 23 responses back from all continents, including Antarctica. These are just a few of the respondents. And what we see is a large range of impacts of LEO satellite constellations on astronomy, ranging from basically nothing in some cases to 100% of science lost. The majority of respondents expressed significant concern and predicted grave challenges to their science. There's significant financial costs ranging in hundreds of millions of dollars, and these could scale up dramatically if and when there are 10 times more satellites. Some of the science losses predicted include, especially in the time domain, fast transients like gamma ray bursts, fast radio bursts, searches for high Z supernovae, and then also very wide field all sky surveys, which have such wide fields of view that it's practically impossible to point anywhere without having a bright satellite cross. Statistical surveys are very vulnerable, that depend on the details of studying morphology of galaxy positions. And there are systematics that are going to be induced from satellite trails that we don't fully understand and may not be able to remove. Of course, there are solar system surveys that operate mostly in twilight, looking for near-Earth asteroids, for example, and that's the time when the satellite impacts are going to be the worst. If there are 20,000 more bright satellites, not just the 2,000 from Starlink, more than half of the respondents said that virtually all of their science would be impacted, and about half said there would likely be a critical failure of their facility. This is a link to the summary of the survey on the AAS website. The AAS has been carrying on very active conversations with satellite operators since that launch. By operators, I really mean operator. It's really just SpaceX. We've had monthly telecons. They've been involved in a number of different activities with the AAS. The focus has been on how SpaceX can dim the satellites and how astronomers can dodge them. Stopping the launches is not on the table. They already have permission. They don't need to ask us for any more permission. They've already got it. We had one telecon with OneWeb, but then they declared bankruptcy, shortly after which they filed with the FCC a plan for 42,000 more satellites. We've had no major conversations with other operators. SpaceX, I'm happy to say, has made some very significant promises not to break astronomy. Elon Musk, the CEO, has said, "I'm confident we will not cause any impact whatsoever in astronomical discoveries, zero. We'll take corrective action if it's above zero." He's promised that there will be no impediments to science, that Starlink satellites will be invisible to the naked eye within 1 week of launch. How can SpaceX possibly do this? They have to change their satellites. Here's what they're doing. First plan, basically paint it black. So this has been tried with one satellite called DarkSat. Did it work? Yeah, it worked. Here we see brightness of 4 satellites before this treatment at about 5th magnitude, and one satellite, DarkSat, after the treatment, it's about a little over a magnitude fainter. So that's good progress, but it's not going to solve our problems, but it's in the right direction. Possibly more effective, VisorSat. This is about to be launched as a test in the next launch, and this will probably be the case for all the future Starlink satellites. Mount a sun shield that just stops the sun from shining on the chassis, so the chassis becomes essentially invisible from the Earth. And then finally, changes to the operating plan for orbit rays. The changes now specify that the satellites will have the very thin edge of the solar panel facing the sun, so there's much less sunlight reflected down to the Earth during the several weeks of orbit rays. Bottom line, SpaceX has devoted significant resources to these technical solutions. But it's not just Starlink. There are multiple LEO constellations planned. Here's a list, and it's evolving rapidly. For example, just last week, this company changed its plan from 117 to almost 1,700 satellites, and they're at altitude over 1,000 kilometers, meaning they're sunlit practically all the time in some cases. And there's no guarantee that all of these, or even any of them, will be good citizens, as we would say SpaceX has been. Just last week, 9 companies filed with the FCC for expanded LEO constellations. Here's a report from OneWeb about their plan to increase to 48,000 satellites. Here is a report on Viasat, which is planning to get into the game with a new 300 satellite constellation. Why the rush? Well, here's one of the reasons. The FCC is offering $20 billion in subsidies to promote broadband space-based digital internet access. Even the military is involved. Here is a report about the Army's investigation of possibly using Starlink for their own purposes. When I consider all of this, my opinion is that LEO satellite mega-constellations pose the most serious threat astronomy has ever faced. You might argue with me. You might say, well, actually light pollution is worse, or radio interference, or space debris. I can't really be sure. They're all bad. Pick your poison. That's astronomy. What about impacts on human experience? It's our job to ask these big questions. What are the stars worth? What is the sky worth? Who gets to decide? Whose sky is it? What is the value to humanity of exploring the cosmos, which we astronomers know has to be done mostly from the surface of the Earth? And if the argument is going to be made by satellite operators that LEO satellite mega-constellations are necessary to provide fast broadband, can we not ask, what are the alternatives? Are the alternatives viable? What's the cost? What about impacts on ecosystems? Here, very little is known. There's no research that I'm aware of about the impacts of moving satellites, bright satellites, on wildlife. But we have some ideas. Here's what we do know. 80% of migrating birds migrate at night, and many or most of them, like these warblers seen near my home in Massachusetts, use the stars to navigate. What happens if all the stars are suddenly moving quickly? We know already that there are upwards of 100 million, maybe a billion bird deaths a year due to light pollution, when birds get confused by city lights and either crash into buildings or drop dead from exhaustion from circling over bright cities, like this yellow-throated vireo that flew all the way up from Central America only to die here in Northampton, Massachusetts. What's going to happen if all the stars are suddenly moving? We simply don't know, but I can only predict it's not going to be an improvement. So what should we do? We have to, astronomers, have to encourage and lead a broad discussion with all of these stakeholders. It has to be an international conversation and collaboration. And it has to lead to agreements and policies, strong policies, policies that control the impacts of satellite constellations. We astronomers are in a unique position of responsibility to do this. It's our job. We're the only ones who are going to do it. We have to do it now. So go out and do that. Join us. When you do, here are some tips for communicating with the public. Share your story, show your passion, keep it simple, and connect with the values of your audience as best you can. And I'm going to leave you now. Well, first here, I want to mention two posters at sessions tomorrow by Pat Seitzer and also Charles Mudd, a lawyer who specializes in space law. And now I'll leave you with a challenge. Find the Starlink satellites in this time lapse from near my home. It'll get a little bit easier when it goes into star trail mode. There's a lot going on here. There are airplanes, lots of different satellites, and the stars moving, of course. And pretty soon you might be able to pick out already exactly where those Starlinks are. So thank you very much. And Sandra and I will be happy to take questions now.
Thanks a lot, James. I'm going to handle the questions and just read them to you. We've got quite a few questions already. I'm sort of going to go back and forth from optical to radio. First question. How is radio frequency used in solar storm prediction? Sandra, can you unmute?
Yes. Well, there are some sensors that are used for looking at the sun and things like that, but I don't know if they're mostly optical. That's not my area. I will have to check on this. If they're optical, that's over the terahertz. So I'm not sure about that. And Jim, do you know what frequencies they use for solar storm?
No, I do not. Sorry.
Thanks.
James, here's a question. How come we astronomers are so late in raising this problem only after the first launches?
Yeah, you know, I ask myself that question all the time. Thank you for the question. I have to say, I hand it to my colleague, Pat Zeitzer, who has been studying satellites and tracking them for many years. On the Light Pollution, Radio Interference, and Space Debris Committee, Pat has been saying for a while, oh, you know, these big constellations are coming. So we all knew they were coming, but we never imagined they were going to be so bright. We didn't, for one thing, we didn't know how big the satellites were. That was not public information. And we didn't know what elevation they were going to be at. So the combination has made them much, much brighter than we anticipated. That was the big surprise. Another reason is the satellite industry evolves on a much faster timescale than we do. You know, we take 20 years to make one satellite. They take 1 year to make thousands of satellites. They change their plans very, very quickly, and it evolves much faster than our regulatory or even understanding science process unfolds. So those are not well matched, and we have been caught behind the ball on this in an unfortunate way, and we're playing catch up now.
For Sandra, does the ITU consider adjacent frequency bands when evaluating satellite filings? For instance, seeing all the recent satellite filings in the KU and KA bands, does the ITU consider interference from OOB emissions in the RAS bands? Yes,
they usually have to comply with no emissions beyond a certain level. So they take, each of the ITU recommendations and regulations, they have a lot of detailed information about the power levels that can be allowed. So yes, they do. The only thing is that sometimes, you know, you have to take into account the aggregate effect of multiple people that have the licenses or assignments.
For James, how should we deal with the backlash from the general public about this problem? It seems the public is backing SpaceX's vision no matter what, deeming astronomers to be fighting against technological progress.
Yeah, that is a really key point, and we have to be sure we are listening to people's values and concerns and issues where they are. We can't necessarily just butt heads against them. If they want fast internet, that's for them to decide. What our job has to be is to promote what we know is the truth of the value of the night sky and the stars, the value of preserving our timeless heritage of the night sky, the value of being able to explore the cosmos, the value to science, the value to society, of being able to answer the fundamental or address the fundamental questions about the nature of the universe. And of course, we always try to do that when we seek funding from national funding agencies, but now we have to do it to actually save the whole field. It takes more people to do it. We have to talk, we have to give public talks, we have to share our passion and love for the stars, try to find ways to connect with values that you know people already have. Maybe somebody really wants fast internet wherever they travel, fine. But they also probably want to preserve science. And you can always tell them, look, Elon Musk himself has said, I love science, I will not break science, I promise I won't. Those are strong values and we should promote those.
Jeffrey, if I can go back to the first question about the RF used for solar storm prediction. My area is ESS, so Earth Remote Sensing. So I had to Google and find that they use all the way from megahertz all the way up to 400 gigahertz. So different sensors use different frequencies to measure spots, to measure magnetic storms. So it's all over the place. I guess depending on the physical thing they're trying to observe is the frequency that they use. The same thing when we look at the ocean or the Earth.
Thank you.
Sure.
Maybe both of you could comment on this comment. I would like to point out that radio transmissions from these satellite constellations can have a deleterious effect on the noise level of radio telescopes.
Yeah, this is enormous, and this is exactly what the spectrum managers at NSF and NRAO are grappling with on a daily basis. So, Sandra, maybe you can talk more specifically, but it's a major issue, and the pressure, our radio protected bands are getting squeezed more and more by these mega constellations. Yeah,
this is a constant, very contentious topic, and I think you can ask later on to the two NSF spectrum managers on the town hall. But this is something that is not new, but it's getting more and more complicated because more and more satellites come. So yes, this is something that is being experienced by many users at NASA, spectrum managers at different communities that use the spectrum.
This is from our old friend Phil Massey. Hi, James, great talk. My solar system colleagues who observe along the ecliptic are used to being photobombed by satellites. Many are in near equatorial orbits, but Starlinks are not. I was astonished when I was observing in the LMC last December from Las Campanas when I had Starlink satellites going through my field of view. That had never happened to me before. I wound up having to retake several fields. So one new aspect of this is the large declination coverage by Starlink. It's not just the numbers, it's the all sky coverage too.
Well, that's a good point, and this is exactly why VRO is looking at losing, in some cases, more than half of their schedulable observations. It covers so much of the sky.
Here's another one maybe both of you can comment on. The FCC has recently declared doubt that Starlink qualifies as a low latency internet, that's less than 100 milliseconds, disqualifying it from the $20 billion incentives. The same should be true for other companies rushing for the money. Could you comment on this?
Yeah, I'm afraid I can't, just because I don't know. I'm aware of that, but I don't know exactly how it's going to come out. I know though that it is forcing most of the operators to lower orbit, which of course decreases the delay time for the communication. So I think that's a major push for all of them. Starlink itself was going to be at 1,100 kilometers, and it has permission from FCC for that, but now in fact it's all at 550 kilometers for a couple of reasons, including largely the low latency. So I don't know if Starlink is going to qualify or not, but the push is definitely to lower altitude. And in many ways, that's better for us because again, they're less in the sunlight, and the orbits will decay naturally in a few years rather than having to be than being up in the sky for 25 or more years.
Well, I think, I mean, that the FCC has this process that I presented that it seeks comments from the public. So maybe, you know, that's a place to go. Maybe they have not have enough interaction, and maybe they don't know about the problems that the radio astronomy community is experiencing.
This one's from the Galactic Times. One, why isn't this covered under some utility regulation like the phone industry? And two, what are the processes for deorbiting for all of these companies? The history of internet communications is of rapid obsolescence. How will these be removed?
They are removed either actively or passively. Passively would be the orbit just decaying from atmospheric drag in the case of low altitude. If they're at higher altitude than that and their lifetime is over for whatever reason, obsolescence or malfunction, then at least all the Starlink satellites have active control. They have ion thrusters that are used first to raise them to their operating orbit altitude of 550, and then eventually to deorbit them, to bring them back down and into the atmosphere. All satellites are required to produce a deorbit plan when they file for permission. And the limit right now is 25 years. They have to deorbit within 25 years.
Andrew Franknoy asks, is there a simple fact sheet or booklet from the AAS summarizing the facts and arguments we should share?
That's a great idea. Not yet. So let me put that on our to-do list.
Yeah, that might be something the committee should work on, because those are the people that are really in the loop about this. All right, we've just got a couple minutes left here. Can't pixels affected by satellites be identified and flagged in software? How about asking SpaceX to fund programmer hours to update analysis pipelines?
Yeah, thank you. Those points have come up numerous times and been discussed seriously and continue to be. In theory, some of us might be able to deal with some satellite trails some of the time, but probably not all of us will be able to deal with all of them all of the time. And we're trying to figure out how to measure the impacts. And it really depends on the particular project. In some cases, yeah, you might be able to just mask it out. In other cases, no, you have to chuck it, the way Phil Massey said he had to with his LMC pictures. So it depends. There are multiple axes to this, these metrics, and trying to measure the impacts is challenging, but we're trying to tackle that now. And as for funding programming time, yeah, that has come up as well. And we are, let's say we're in close discussion with folks from SpaceX on a regular basis. And there is the possibility that they will perhaps increase some support to programming. That's not going to work in all cases. We think about big projects like Vera Rubin Observatory. They already have dozens of programmers working on the algorithms for the scheduling and the data processing and so on. Not every observatory has those resources, and it won't be a one-size-fits-all solution. So it's complicated.
Won't rolling the Starlink satellites impact their collection of sunlight and hence power? Would this be a maneuver the satellites would perform daily? If so, how realistic is it to expect Starlink to do this?
I think they're already doing it. I asked the same question. It turns out it's just not a problem. Remember, it's a 90-minute orbit. They have to worry about the roll only when it would be interfering with observations. Yes, they can roll it numerous times during an orbit, and it's only during the orbit raise. So the loss of solar power during those brief times is not an issue for them.
Here's a good one. What's the color of the SpaceX satellites?
Muchas gracias, Jesus. The color is sunlight.
Good point. Okay, we're going to wrap this up. I'd like to thank everybody for answering. Obviously, the speakers can answer some of these questions offline, and feel free to try and get together during the meeting and discuss this more fully. But I'd just like to thank our two speakers for two really interesting and timely talks. Thanks a lot.
Thank you,
Thank
Jeff.
you. Thank you for the invitation. Have a great day.
All right, I'm going to stay on and answer some of these questions. And Sandra, I hope you will too.
Yes, yes. I've already typed some answers.
You have. Okay, I'm sorry. I have not been able to multiplex quite that efficiently.
Thanks to both of you.
Okay.
I mean, there's obviously, as you can see, a lot of interest in this.
Yeah.
Good. I'm glad there's a lot of
That is
interest.
good.
So
All
you, James and Sandra, are you going to type the answers to your questions?
Actually, well, I don't know what's best, typing or speaking. How do we know if these questioners are still online or not?
There's 39 people. Sorry. Go ahead, Jeff.
Do we know they're still online, Elizabeth?
Yeah, there's
Yeah.
39 people still. Oh, wait. 140 people still, and they can hear me. I'm assuming, right, Brian? We
That
have
is
two.
right. Maybe verbal is probably the best way of going. There's still quite a bit of the audience left.
Okay.
Okay, so just go ahead. How much time do we have left, Brian?
We don't have another session using this webinar for a couple of hours now, but that would be up to the up to Elizabeth's judgment.
We
Okay.
have two town halls starting right now. Keep going, and I'll pop in a minute. Okay. I want to check with Kevin.
Okay,
So
should we take them by order of appearance? I don't know.
Sure. If that's okay with you, I think it's a good idea. I'm
just go
scrolling
ahead.
down.
I'm going to leave you guys to it, and Brian can tell
Okay,
you
Jeff.
when you have to get off the Zoom.
All right. Thanks, Jeff.
Anyway, very nice to
Thank
see
you,
you,
Jeff.
both of you. Nice to
Bye.
meet you, Sandra.
Nice to meet you too.
Uh,
Okay, bye. So the first one that I see is how come we astronomers are so late in raising the problem?
Yes, that one
Oh,
came
yeah.
already. That one.
Well, but I think, I mean, I've been working with this for quite some time. And I know at Geneva, there have been people, astronomers, raising these questions. So maybe not as many as it should have been, but they have.
Again, we failed to anticipate how bright they were going to be.
Mm-hmm.
We had no idea it would be that, and it's just developing so fast. And
Okay.
as a culture, we astronomers are not so quick to change. Think how long it took for exoplanets to catch on.
Yeah, I have exoplanets on my necklace. But
And the radio spectrum on your scarf.
Oh yeah. So I'm gonna click dismiss on the first one then.
Okay.
Okay. So the second one. How should we deal with the backslash from general public about this problem?
Yes, we
Did
discussed
we
that
answer that one?
Yes.
Okay, so I'm gonna dismiss that one. Is there a simple fact sheet or booklet from AAS?
We discussed.
Okay, so I'm gonna dismiss. Why isn't this covered on the song utility?
We discussed.
Okay.
Yeah. And Phil Massey, we discussed.
Okay.
This one we discussed.
Okay.
What can astronomers learn from climate scientists on communications of risk to sustainable environments? That's a great question. I would say the major difference is that the field of climate science is highly evolved. We know very deeply and in great detail what many of the impacts will be to many of the world's ecosystems from climate change. We do not know at all what the impacts will be of satellite mega-constellations on such ecosystems. They might be minimal, but we don't know. I mean,
yeah, I wanted to mention that when you mentioned the fact about the bird, I also read an article about the effect of Christmas lights on populations of fireflies. It's so many things we have no idea the impact and the repercussions they have on nature.
If we rely on our understanding of light pollution, then there is a large body of science and growing. Mm-hmm. And essentially every species of animal that is studied turns out to be vulnerable to light pollution. But whether they are also vulnerable to moving stars from artificial satellites, we just don't know. Mm-hmm. I think the larger question, what we can learn about communicating with the public, though, is really relevant. And one of the questions is asking me to elaborate on my suggestion that you connect with the values of your audience. I really think when you talk to the public, or you talk to decision makers, or you talk to students in a classroom, you really have to think hard about putting yourself in their shoes. Think about what they already know, what they already care about, and try to find some way to connect with those values and those things that they already know and care about, instead of just telling them, you should care about this because I do. Mm-hmm. So that's a sort of general communication rule that I try to employ whenever I can.
And I found also when I communicate that it's also good, unfortunately, to mention what's the $sign value, because some people are moved by what's good for nature and others are moved by what's good for the economy. So that way you get both. Next question. You want to read it out loud?
Sure. Can the FCC be approached to request they give tough requirements for approving satellites that address astronomy concerns? Maybe Sandra, since you know the process so well.
The FCC, people cannot like raise the phone and call the FCC to do that, but they have that process. That's the only way they have when they, or they can also express through international bodies like IUCAF. I don't know if you know what is IUCAF, but that's one. Through CURV, maybe, which is the National Academy's Committee for Radio Frequency. IUCAF is international. There's also the IEEE FARS. But through the FCC, it would need to be through the rules and comments process that I explained. So that's all online. You go online and you see, hey, they want to touch my frequency. You have 60 days to reply. And it could be replied as a citizen, it could be you replying as your institution, as your laboratory, but that would be the way. If they don't hear from you, they assume everything's fine. And usually the companies do answer, but if the scientists are too busy doing experiments until everything fails, then, you know, but the process is there. So that's the only way that I can think of. Next.
Thanks, Sandra. There's a question from Peter Kochis. I'm not sure if I'm pronouncing that right. Will an increase in satellites create a push for more space-based telescopes for research? Yes, I would say so. And in fact, Elon Musk has said, well, you should put all your telescopes in space anyway. Well, fine. We love space telescopes. That's great. Of course we use them. But
it's so expensive.
They're so expensive. And just to put that in perspective, Starlink is roughly a $10 billion project. I don't know exactly, but I think it's on that order, it's on that scale. That's about the same scale as James Webb Space Telescope. So I just can't see SpaceX funding significant changes to astronomy to move all our big telescopes into space. We just can't do it. We're already struggling to get an 8-meter telescope or a 6-meter telescope into space after decades of work. And we're just going to rely on ground-based astronomy for the foreseeable future, for decades to come, for any large aperture use. What are these universal broadband access services going to cost the average consumer to use? In other words, how much does it cost to use Starlink? The numbers I've seen are something on the order of $100 a month. But it has not been, that's not coming from SpaceX. That's just, you know, industry policy wonks trying to figure it out.
Okay, and it's also asking you to put the posters in the chat. Did you do that?
Posters in the chat.
The two posters that you mentioned on your presentation.
I
so
see.
if you could click on the chat and put those so that everybody can see them. Because if you answer here, they don't all.
Yes. Okay, very good. I will do that. They are 31107. I'm going to just cut and paste.
Okay. And in the meantime, I'm going to read another question. Whenever we take optical emission spectrum of 13.56 megahertz RF, the spectrum gives huge noise, especially between 200 and 500 nanometers. Why and how can we reduce this noise? So the question is a little bit confusing for me because it says we take optical emission spectrum and then they mention a frequency that is not optical, which is 13.56 megahertz. That's microwave. So if Reza is still there, if you could explain to me, I'm an engineer. For me, 30 megahertz is RF. So what do you mean taking optical emissions? If you could further explain, and maybe in the chat, I don't know, let me see. Next one is, I would like to point out that radio transmission from this satellite constellation can have the deleterious effect on the noise level of radio telescope.
Yes, very much so. That we discussed.
That's shown in your presentation, right?
Both.
Yeah.
Let's see, one question was
That's
answered
right.
by Pat.
Okay.
Why not do a program of presenters like Al Gore's Climate Reality Project? Yeah, sure. Well, you know, a number of us are doing as many presentations as we can currently, but maybe James Schweitzer, you'll start doing some yourself. Courtney Crawford asks, how feasible is it that a new detector mechanism or a new observation strategy would help to combat the impact on observations? I am sure that we are going to need to develop new detector mechanisms and new observation strategies because the satellites are going up, whether we like it or not, and we are going to have to deal with it. So there's no question we are going to have to adapt our own strategies and technology. For example, CCDs are probably not as good as CMOS for a number of reasons that Tony Tyson at VRO can probably answer better than I. The CCDs have very slow readouts. There are charge transfer issues. So for sure, we're going to be adapting to the new reality.
And there's many mitigation techniques that engineers have designed to try to reduce the amount of RFI combination techniques and, you know, filter design, but it comes at times with they really have to do, you know, blanking of data because there's no way to recover some of the data. So, but more might be to come.
James, you gave an estimate of the degree of mitigation provided by DarkSat. Could you estimate what that might look like for visor and orientation approaches, or not until yeah? I don't know. The predictions from VRO and SpaceX are it's going to be at least another magnitude, probably more. So that means going from 5th magnitude to something like 7th magnitude. And that would be enough that they're no longer visible naked eye, and they are maybe just on the edge of where VRO can deal with them.
I've heard of constellation of 60,000 satellites coming. So
yes, yeah,
that's the future, I guess.
And 60,000 satellites at, even if it's magnitude 8 or 10, that's far below naked eye, but those are still going to saturate a lot of detectors or terribly complicate most science programs. Let's see, the question, for the Vlasov simulation, which is the simulation of the Starlinks moving in the Big Dipper, do I know what latitude? I do not. And how does it vary with latitude? Is it worse at high north and south latitudes? It's quite complex. It depends, let's see, Pat Seitzer, maybe you can answer this if you're still online, or ask Pat for more details. He is the expert on this, but it does depend on latitude, largely because in the high latitudes, in the twilight hours, you know, the sun is setting at an angle like this compared to the horizon. And so twilight goes on basically all night long. And so it's much easier for the satellites to be in the dark from the high latitudes. Closer to the equator, everything is basically, you know, the sun is setting vertically like this. You go into nighttime very quickly. Okay. As a deep lover of the sky, also, full disclosure, also a satellite observer. This is Joel Weisberg, also a satellite observer since 1964. I do not feel that more bright ones will harm my aesthetic appreciation of the night sky. This is, of course, totally separate from the issue of terrible effects on science observations. I wonder if many other amateur sky lovers also don't mind and therefore would not be particular allies. That's a good point. It's clear there's going to be a variety of impressions and responses to the phenomenon of a changed night sky.
Yeah, in fact, I know people who are fans of Iridium satellites because they love how they, you know, look, and they follow them. So, yeah.
Here, Mahmouda Afrin Badan. Hi, Mahmouda, former Mount Holyoke student who worked with me here in 5 colleges. And Sandra, you were at UMass, yes?
Yes,
okay.
I was.
Mahmouda writes, I did a little survey here in Australia where I asked a bunch of random people without college degrees, but in trades professions, what they think about Starlink filling your skies with satellite, and if they think 5G is worth it. Most of them are using 5G on their new phones, and they said 5G is not worth it. They're worried about what that's doing to the skies and the repercussions. Right. One thing to keep in mind, what is all this fast broadband internet used for? If we're so convinced that it's driving the economy and that people need it, and the predictions are that by 2024, I think, more than 80% of internet traffic will be video streaming. So what we're talking about here is, massive changes to the sky and to astronomy and to our heritage to do Netflix or remote conferences like this. And so we definitely, it has to be part of the discussion. What are the various values to society of all these competing interests?
Yeah. We have to set our priorities as a society, I guess.
Can we imagine a partnership with SpaceX? What astronomy can be done? Whoops, I just lost it. With an 8-inch telescope, there it is, 8-inch telescope and CCD on the upward facing surface of each of these 40,000 satellites. What a cool idea. Wow, I had not heard that one before, Stephen Lawrence. Put a telescope on each of the satellites. Nice. Okay, we'll put that in the hopper. I would say,
the only thing is that I think every pound of load on a satellite costs like $1 million. I don't know if the cost is smaller. I think it's smaller for SpaceX, but there is some cost, more combustion fuel or something like that.
We do have a partnership in the sense that they have been openly discussing with us, and we have built up something of a collegial relationship with information sharing. And as I said, they are participating in numerous of our AAS activities. But of course, that's only one satellite company.
Good. That's good. But it's a strong satellite company.
Megan Donahue wrote, I think it's important to understand that what impacts VRO impacts the whole system. Our system depends on science from the system, not just one telescope. Thank you, Megan. Absolutely true. It is not just a telescope by telescope problem.
Mm-hmm. True.
Whatever VRO produces ripples all the way through all the follow-up that all other projects will do, and vice versa. Deeply interrelated system we have. Okay. Let's see. It says for James, could existing environmental law, and Charles Mudd has responded to this, environmental law force an environmental impact study before further launches? Could the threat of such a lawsuit delay or be used to force better cooperation from these companies? Yes, actually, the International Dark Sky Association, with help from Charles Mudd, did. The EPA is currently revising its code, and IDA and Charles Mudd actually put in a note to say, hey, you should consider the effect of satellites on the sky as part of NEPA review. Sandra, something for you in here that you want to answer?
Let me see. Let's scroll down. Which one? From Mark Morrison?
Any of them, sure.
Oh no, let me read them.
Mark Morrison says, yeah, $100 a month should be a non-starter for the vast majority of people. True. I think so. SpaceX has not advertised this yet. We're all just surmising. We're just guessing. But I think the plan is provide it free or cheap to most people in the world. But their market is, there has to be a business model. The only way this works is if they get money for it. And the business model is charge people in North America and Europe. And the first section of the world that is going to get service from SpaceX, Starlink, is North America, US and Canada mostly.
I would think also that they might gain from ads. So even if it's free for people not in the US, in other continents, if you're looking at a video, every time you get an ad, that they get some money from it. I would say that's part of the way they get funds. I don't know.
It really is the way much of the internet works.
Yeah.
Felix Lockman says, hi Jay, says, to put our work into perspective, a few years ago, I visited with US Senate committee staffers to urge astronomy funding, and the chief staffer said, We love you, astronomers, but we hear from you only once a year. I get a call from Lockheed Martin every day. Right. Yes.
There
thank
you go.
So that is a call to astronomers to be local, to build relationships with your local representatives and tell them what your concerns are. You should be talking to your local reps regularly, several times a year at least. Get to know them. Jamie Carter writes, even if VisorSat is successful, won't the light from celestial objects and events still be blocked and data lost? In other words, will the satellite block things? Surely VisorSat being dark merely makes it invisible to stargazers, not astronomers using big telescopes. Right. If it goes from fifth magnitude to 10th magnitude is still very bright. We astronomers on big telescopes, we avoid a 10th magnitude star. It's still too bright. And a satellite will likewise be a problem, but it's less of a problem. We're just trying to minimize the problems. Won't the light from celestial objects be blocked? In other words, will the satellite occult stars? Yes, but only very, very briefly. They're moving at a rate of about ½ degree per second across the sky, which means they're in front of a single star for a small fraction of a second. And we think that for most cases, that is going to be negligible. What can amateur astronomers do to help? Join the International Dark Sky Association and get involved there, and give talks yourself. Get people in touch with the night sky is my advice. Do night walks, do astronomy presentations with people. Spread the word in your social networks. Well,
I think this, let me see, is there anything else?
hello again, Elizabeth.
Hi, that was amazing. I'm not a
Thank you.
scientist, but I think it was fascinating. Thank you so much.
Thank you, Elizabeth.
Sure, thank you.
Do you think you've gone through most of the questions and answers?
Most of them. And for those we haven't, if you didn't get your question answered, feel free to contact me offline. You can find me easily in the usual ways.
Yeah, me too, if there's anything that I can help with. Thank you for your attention.
Thank you, everybody. Thank you, Elizabeth. Thank you, Sandra.
Thank you. Thank you, James.
All right. I
Thank
hope
you.
everybody enjoys the rest of the meeting
Yes.
and,
Yeah.
in good health and safety.
Fabulous.
Thank you. You
Bye
too.
all.
Bye-bye.
Bye. Thank you.